Okay, well, maybe we'll get started. So I'd like to welcome you all to the annual Robert F. Christy lecture. Bob Christy was born in 1916. He was orphaned at age 10, raised by his grandmother, but at the end of middle school, he won the governor's gold medal, so he could skip high school and go directly to University of British Columbia, where he got his bachelor's degree in mathematics and physics. And then he had a friend, George Volkoff, whose name may be familiar to relativistic astrophysicists, who went to Berkeley. So he decided to go there too. And they both worked with Robert Oppenheimer, who at the time was commuting between Berkeley and Caltech. He got his PhD in 1941, working on the theory of muon spins and muon pair productions, muon showers, and showed that it was not, in fact, the Yukawa particle, as some people had originally thought. And then in 1942, Oppenheimer persuaded him to join the Manhattan Project. And there he did a great service for theoretical physicists. In 1943, he predicted that though you would need 575 grams of uranium-235 to go critical in the first nuclear reactor. And the next year, criticality was observed with 565 grams. And at that point, people thought, oh, these theorists just do order of magnitude, but they realized they actually could get numbers correct. So that year, he also became a US citizen. In 1944, he was part of the T1 group that investigated how to trigger criticality in plutonium, not uranium, and designed the Christy pit, or the gadget, which was used in the famous Trinity test and in the Fat Man bomb used at Nagasaki. The Hiroshima was a uranium cannon. Then after World War II, Oppenheimer was very busy with lots of meetings on the East Coast, so he decided to move to Princeton. And Caltech then didn't have any theoretical physicists, and so Oppenheimer recommended Bob Christy as his replacement. So he was hired. He continued working in various parts of high energy physics, campaigning for atmospheric test bans. And in astrophysics, he's best known for some work he did in the early 1960s, working out what is it that makes Cepheids and RR Lyrae stars actually pulsate, using the techniques of new radiation hydrodynamics, which had been developed for understanding radiation hydro of things that go outwards one way and don't have enough gravity to bring them back in. So he did both directions, and as a result of that, he was elected to the National Academy and won the Eddington Medal of the Royal Astronomical Society. So I think Dan will say a little bit more about this. I just wanted to point out that the computer that he used for this was an IBM 7094, which was the first computer which had transistors instead of vacuum tubes in it. The price inflated from 1960 would be about 33 million, which I think is roughly the same price as the computers that Dan uses for radiation hydrodynamics. But you'll notice the gigahertz, gigaflops, and gigabytes of memory have increased by 9 or 10 orders of magnitude for the same price. So Dan will say a bit more about that. When I arrived at Caltech as an undergrad, he was the vice president and provost. And when I was a sophomore or junior, he became the acting president after the former President Harold Brown was appointed the US Secretary of Defense. I just wanted to maybe mention that things have changed a bit in politics. So Brown was proposed by Jimmy Carter as Secretary of Defense. The Senate appointed him on January 20th. The Senate approved his position on January 21st, and he started work on January 22nd. Things don't seem to go that fast anymore. In 1986, he retired from the Institute, but he didn't retire from work. He headed the NRC Committee on Nuclear Dosimetry with doctors and nuclear physicists, biophysicists, understanding the effects of radiation on humans in Nagasaki and Hiroshima, for example. In 1973, he married a theoretical astrophysicist, Inga Juliana Sackman, now Inga Juliana Christy, who's, I'm pleased to say, in the audience. They had two daughters who I'm pleased to say are also in the audience. One of them is shown rather young. That's Elia, and the other is Elia and Alexa. And you notice that they were brought to the Caltech trustees meetings to help raise money, I think probably by looking adorable. So while Bob Christy was the provost and president, he did a number of things which have remained at Caltech. He instituted the core requirement in humanities and social sciences, which all subsequent undergrads had to do. And he also introduced undergraduate women for the first time, 1973, and the first tenured woman faculty member. And I think Juliana's persuasion had something to do with all of those. Okay. He was, as I mentioned, he was lured by Oppenheimer to Los Alamos, and one of the ways that Oppenheimer persuaded him to go was to offer him a half share of a horse. Lloyd Williams had the other half of the horse, and they used to have arguments at cleaning time of who was responsible for the emissions from the backside and who from the front side. So, but Bob Christy was still jumping horses, whitewater rafting, climbing, and doing long distance hiking in his late 80s, early 90s. So something to inspire all of us. Okay. Now, so let me say a little bit about our speaker today, Dan Kasen. And before I forget, I just want to mention that if any of the students or postdocs here get inspired by Dan's lecture and want to go work with him at Berkeley, Dan and I for many years have been co-PIs of a Moore Foundation grant whose purpose is to encourage interactions of graduate students and postdocs between Berkeley, Santa Barbara, and Caltech. And if you want to go work with Dan for a month or 2 months or something, come see me afterwards and we can arrange it. So Dan got his undergraduate degree from Stanford in 1997 and his PhD, just like Bob Christy, from Berkeley in 2004. Then he was a prize postdoc at Johns Hopkins, a Hubble Fellow at UC Santa Cruz, working with Stan Woosley. And in 2010, he returned to UC Berkeley as a faculty member, where he's professor and director of the Theoretical Astrophysics Center at UC Berkeley. Now, I mentioned that Bob Christy's pioneering calculations explaining how Cepheid variables and RR Lyrays worked, and the astronomers will know that those are the first step in the cosmic distance ladder. Dan is best known for his radiation hydrodynamic calculations of the brightnesses of the last step in the cosmic distance ladder, namely supernovae of all types, 1As, 1Bs, 1Cs, type 2s, and including ones which are not just nuclear powered, but powered by central engines like magnetars and accretion. And he's also very well known for his calculations of not supernovae, but their smaller relatives, the kilonovae, which are the electromagnetic outcomes of double neutron star mergers, and even on tidal disruption events. And today he'll tell us about neutron star mergers, kilonovae, and kilonova impostors. Yes. Oh.
All right, thank you, Sterl. Thank you so much for having me out here and spending your time listening to me. It's a real honor to give a talk in honor of Robert Christy. So thank you, especially to the family who had me here and came all the way out to listen to the talk. Hopefully it'll be somewhat interesting enough to keep your attention and make the drive worthwhile. Yeah, I knew of Robert Christy, but I didn't know much about him until I started reading some of his old papers and interviews with him. And as Sterl said, he did such an enormous number of amazing things, working on the Manhattan Project, advances in nuclear physics, and then in astrophysics. and Sterl alluded to his work on Cepheid stars. This is one of them. Again, crucial stars that Hubble used as candles to measure the expansion of the universe, but which at the time and for long after, the theory of how they work was poorly understood. And Professor Christy did pioneering work in trying to explain exactly the pulsation and radius and brightness of these events. But that work stands for till today. But even more impressive is how he did this, pioneering computations in nuclear astrophysics, multiphysics calculations, where he solved the equations of hydrodynamics, radiation transfer, the equation of state of matter, its ionization state, and the opacities that came out of it, which all are crucial for this pulsational behavior. Solved all those physics equations at the same time using a computer. This was the computer that Sterl mentioned. I think I got the right one. It had 100 or so kilobytes of memory. And yet he was able to do these calculations on this, and what were some of the first numerical calculations ever done. So it's a real pioneering work that kind of laid the groundwork for all the things I'm going to tell you about, which are kind of just extensions of that. A lot follows from that initial foray into scientific computing. He was also his wife Juliana sent me a bunch of wonderful pictures about him as working on the farm, and his work as a great athlete, skiing, riding horses, as Joel said, later in his life, playing tennis, and so on. And actually, this tennis racket kind of reminded me of this computer in that it looks high tech for the age, but kind of small and old-fashioned until today. But I got a sense looking at this that he would still be able to crush me in tennis even with my fancy racket today. So it would have been fun to be out on the court with him. I'm going to tell you about neutron star mergers and kilonova and simulations that are done of that sort. The bigger picture scientific questions, well, there are many of them for neutron star mergers, as you probably know. They're sources of gravitational waves. They're regions of intense gravity and density, but they're also crucial to the formation of the heavy elements in the universe and part of that story. And here's the distribution of elements in the universe, and there's great astrophysical stories to tell for all this chart. And of course, Big Bang only made hydrogen and helium and trace amounts of other small elements. Rest were made in stars and stellar explosions, some massive star explosions. But this peak here of iron was made mostly in these kind of stars that Sterl mentioned, the type 1a explosions of white dwarfs. I won't talk much about that here, but I wanted to mention one thing, might come back a little bit towards the end. But these white dwarf stars are carbon and oxygen and thought to be accreting from a companion star. And somehow or another, something triggers an explosion that runs away in a thermonuclear runaway, burning up the entire carbon-oxygen white dwarf in a matter of seconds and leading to a supernova. And this is the kind of situation that can be modeled using the kind of multi-physics numerical calculations I mentioned. Here's work done by Ken Shen and Sam Boos, having a carbon-oxygen white dwarf that's created over time a layer of helium donated from the companion star. And this is you can ignite a detonation at the surface to trigger the surface explosion of that helium, which then wraps around and compresses the carbon-oxygen white dwarf, creating a high-density region at the convergence, which then goes ahead and detonates right there, the carbon-oxygen white dwarf, blowing up the entire star. And in the process, making a lot of iron group elements, nickel 56. This is where the iron in the universe comes from. So I thought this was interesting to bring up. Robert Christy is famous at the Manhattan Project for his suggestion of the Christy pit, which was a sphere of plutonium that he said if you compress it, it will reach some sort of convergence point, which will explode the entire pit. In that case, fission instead of fusion. And he made a remark in that paper on the Cepheid variables, how it was remarkable that the numerical methods that were developed at the Manhattan Project were now being used to explore questions in astrophysics. And his idea here is still becoming the most prominent theory of how these type 1As explode and being studied in some detail using these numerical calculations. Well, I won't say too much more about that, but here's an example of a type 1A supernova, and I just want to mention that in these kind of stellar explosions, that explosion lasted a few seconds. We don't see the explosion itself. We see the aftermath, the ashes and debris that gets shot out, and it's highly radioactive and glows quite brightly for some months afterwards. In this case, glowing from the decay of this nickel-56 production that decays down to iron over periods of months and years. And that leads to this bright event that's, brighter than the entire galaxy that it's sitting outside of. We can model that light curve and show that the bigger the star, the more nickel, the brighter the event. And compared to observations, we can model the spectrum and actually see the iron being at its production site, proving that this is where the iron is created and understand the conditions under which it was first produced. But going back to this, today, rather talk about the elements that are heavier than iron that, while not so abundant, are quite interesting from an astrophysical point of view. They can't be produced in the similar sort of fusion event, which only stops maybe a little bit heavier than iron. But the idea of how they're created has been around since the 50s through a process of neutron capture. If you create some conditions where there's an excess of neutrons, quantified by this electron fraction, the ratio of proton number density to baryon number density. If you start with some gas of neutrons and protons and let it decompress, it'll form into alpha particles, and the alpha particles will fuse into heavier elements like iron and heavier seeds, but you'll be left with some excess of neutrons at the end of the day. And then you can go farther than these seeds by processes of neutron capture onto those nuclei, building it up, followed by a beta decay, turning the neutron into a proton. And in that way, walk yourself way up all the way on the periodic table through a repeated process of this. And the rapid of the R process is just these neutrons capturing faster than they beta decay. All right. So that's the idea. You can watch this happen in practice by doing R process reaction network calculations, following all the reactions, and they go through the thousands of nuclei that are on the charts of the nuclei. Here's all the different nuclei, and these are the stable nuclei. And if you start with very neutron-rich conditions, you follow a path through neutron capture that's very neutron-rich, close to the drip line, and repeated neutron capture builds you up all the way to the heaviest elements, which will then subsequently beta decay back down to stability. If you're mildly neutron-rich, you'll only have enough neutrons to kind of build yourself up to the lighter R process elements before you fizzle out. So the full distribution of elements heavier than iron requires conditions that are both very neutron-rich and mildly neutron-rich in sites that can produce that. So that's the process. The question, of course, is where does this happen in the universe and how? Naturally, you need neutron-rich conditions, so the notion is to look for regions that are heavy in neutrons, in particular neutron stars. So neutron star mergers where you may liberate some neutron-rich material from the stars in the collision. Core collapse supernova, or certain variations of them where you have high rotation or high magnetic fields, and you blow off some material in the process. There's several others. This was the picture I had of a accreting white dwarf that could explode as the type 1A supernova, but on other conditions, the accretion may cause it to collapse into a neutron star, potentially producing our process, something we're working on, but I won't really have time to talk about today. So we can use the numerical methods to try to understand the physics in these different environments and see if they correspond to things that we see in the universe. I think it's a physics audience, so I'll try to keep it general and give you a broad overview, but let me know if there's anything that's unclear as I go along. So, the simulations have to cover a lot of phases of the event, and so require a lot of physics and a lot of different codes. Once you start with the initial conditions of a binary merger, you need to solve in the merger the hydrodynamics of the event with gravity, ideally general relativity, treat the dense matter that you have in neutron stars, neutrino physics. Neutrinos are crucial in these very dense environments to transport energy and to change the electron fraction, nuclear reactions, potentially magnetic fields. There's really one code that can simulate all of that over all phases of the merger. So usually it's several codes capturing different phases of the event. And you can solve, as I just showed, the reaction networks using codes. And then finally, you can look at the aftermath of the explosion, where you have this debris cloud flying out, heated radioactively, and try to calculate its equation of state, its ionization and excitation, and its atomic opacities, and how the photons diffuse through that. Okay. So we're looking at, in this case, neutron star mergers to give you the scales. They start to merge when they're sort of tens of kilometers away, and they're orbiting each other at a few tenths of the speed of light. Periods of milliseconds, so it's sort of the time scales that you want to simulate to do the merger itself. And again, gravitational waves are at the merger point of the kilohertz. You probably are aware, in 2017, we had the one event that showed us both a neutron star merger in gravitational waves and in electromagnetic radiation. We'll talk a little bit more about that as we go along. So let me show you some simulation work that's looked at various aspects of the merger and how material, neutron-rich material may be liberated. Initially, you may liberate material in the merger itself. Two simulations, and nice work here by Elias Most, showing a neutron star merging with a black hole. And as the neutron star approaches, it gets tidally ripped apart by the black hole, and you fling out a tail of material from the neutron star. And you work with Francois Foucault doing two neutron stars. Similar processes go on, but you have multiple tails. And again, fill this equatorial region. If you want to study this material, well, some of this material remains bound to the central remnant, and some of it is ejected. So you have to follow this dynamics over much longer time scales to see what stuff finally makes it out and what its structure looks like. So we could do this with further hydrodynamics codes. And here for some of these neutron star merger simulations of Foucault, you can see the distribution of velocity of the stuff that gets ejected. A few tenths of the speed of light is not surprising given those are the kind of orbital velocities. And with these electron fractions that are quite low, given that this is mostly liberated neutron star material. The total masses involved are rather small, only maybe 10 to the minus 4 to 10 to the minus 3 solar masses, whereas the neutron stars themselves are order solar mass. But there's other ways to liberate mass that may be more important. One happening immediately after the merger in a phase that's been a little less studied, where most of the mass is in this merged remnant, which is likely to eventually collapse to a black hole, but may for some period of time stay alive as a neutron star. Even if it's above the maximum mass that a neutron star can have, it can be held up through rotation, differential rotation, or thermal pressure, maybe for tens or hundreds of milliseconds or longer before it finally succumbs and collapses to a black hole. And during that phase, material from the surface of the neutron star can be blown off. It's radiating neutrinos like crazy as it's hot from its merger, and that can blow off neutrinos, blow off matter from the surface of the neutron star. And so here's some recent simulations we did led by a graduate student, Lika Sippens-Gromeyer, showing matter getting blown off in this process, mostly along the polar regions, as the equatorial regions are still pretty dense with material from the disruption, and showing electron fractions that are actually quite a bit higher than the stuff that was initially flung up to 0.4 or greater. That's a result of the neutrino processes from this radiating neutron star. Those neutrinos, flip proton and neutrons and drive you to a more symmetric situation. And eventually that neutron star, if it lasts any time, it may eventually collapse to a black hole. How much material it blows off in this wind will depend on how long it survives as a neutron star. Eventually it may collapse to a black hole, but still interesting things can happen after that fact, as some of the material that would remain bound is in the disk around it and can continue to accrete, but at the same time be blown off away from the system. And that's been studied by a number of groups. This is some work recently by Gottlieb, simulating that accretion process. The orbital period of this gas is again on the order of milliseconds, but it takes longer for it to accrete onto the black hole because you have to have viscosity or friction sort of rubbing against each other to drive the material to the center. And given the typical turbulent viscosities you have here, you might have a time scale to accrete of 100 times the orbital time scale, so seconds. So this is happening on somewhat of a longer scale. And in the process of this accretion, you bring a magnetic field towards the black hole, wind it up and drive these relativistic jets. Low density, but material moving at very near the speed of light. But you also blow off material, subrelativistic material, in this disk as it's heated in this viscous accretion process. And actually, a good fraction, maybe half of that disk may be blown off in this process. This may be the process that gives you the most mass ejected in the neutron star merger event. The relativistic jet can go on to interact and produce a burst of gamma rays that you would naturally expect to last a few seconds while it's in this very rapid accretion phase. And of course, those sort of gamma ray bursts are seen, and gamma ray burst of the order of a few seconds was seen in this 2017 neutron star merger event. So those are the various phases of ejection. After you have the mass ejection, you have this cloud of debris, whatever its structure is, that's going to expand out quite large. But before we can see anything from this debris, it has to expand out to where it starts to become translucent and light can escape from it. But it's moving fast. At a day, it's already about the size of the solar system. Densities have dropped by orders of magnitude. And it's radioactive. Beta decay and other processes are keeping it hot and dumping a lot of power into it, which can ultimately lead to the radioactive glow, keeping it sort of thousands of degrees. And we want to simulate that phase. I won't go into details of the process, but we want to solve for the process of that heating, the state of the plasma, and the physics of how radiation is transported through that. So basically solve a Boltzmann-type equation for radiation transport. Involves solving the matter state, which may be in equilibrium or non-equilibrium, and involves a lot of atomic data, and then using that to calculate the emission and absorption of this gas over time. And the atomic data that goes in there requires us to understand the structure of the atoms that are produced, all their different levels and bound transitions, which contribute to their emission and absorption. Of course, the stuff that Robert Christy was working on included hydrogen and its ionization state, which was quite important to the opacity of those Cepheids. Iron, which appears in a lot of astrophysical contexts, is an incredibly complex atom, a lot of transitions and a high opacity. So even if its abundance is low, it can really dominate the opacity of something like a Cepheid star. But in these neutron star mergers, we may eject these very heavy elements, including lanthanides and actinides that have very complex electronic structures, huge numbers of levels, and extraordinary amount of lines. And so the actual opacity we have in this fallout plasma is usually dominated by these line transitions that are very high in the optical and UV and start to fall off some towards the infrared. All right. The atomic data is quite uncertain for these heavy elements as they're not so well characterized, but we have a general sense of their behavior through atomic structure calculations. And so putting that all together, you can make a prediction of the luminosity from some cloud of radioactive ejecta from a neutron star merger. Go here. And see if I can move forward. Here's the spectrum just generally starting out with blue light from this light R process material, the polar regions, over time turning redder and redder as those very heavy element opacities start just absorbing all the optical and UV light until most of the emissions coming out in the infrared. And so the heavy elements tend to absorb optical light and emit in the infrared. We have this nice color coding that if you have mostly heavy elements, you're going to get mostly infrared light. If you have lighter elements, you're going to get bluer light. And we can use that as a diagnostic to determine the composition of the material that we may see. Well, we have one great example of this, the 2017 event, the neutron star merger that was seen in gravitational waves and was then found in optical and infrared light. And here's some of the data from that. Is incredibly well sampled across from the UV optical into the infrared. And here's just an example of some modeling done by a graduate student, Daniel Brethauer, showing a model fits for certain parameters to the data. And while things aren't perfect here, you see some modest agreement in different bands with some disagreements, say it more at later times. All right. So the general picture of these afterglows from a neutron star merger event are consistent with this idea of having some heavy element radioactive cloud emitted in the process. And we can diagnose some the amount of the yields of heavy elements and their gross composition. Okay. There's, of course, a lot of uncertainties in this. There's one study showing as you vary the inputs of atomic physics between various groups' data, how much these light curves can vary. There's also uncertainties in the nuclear physics and everything along the way. But the general paradigm seems fairly robust as a lot of the physics, stays as you have these very complicated systems. It breeds a certain simplicity. There's so many elements and so many atomic transitions that a lot of the uncertainties get sort of averaged over and keep our uncertainties in some limited range. Well, that was in the one kilonova that we really have excellent data for from 2017. And it was somewhat of a success of the theoretical modeling in that it could basically explain its rough properties. There was a quote I read in one of Christy's interviews where there was someone was asking about his prediction that Sterl mentioned of the critical mass and how he got it so close, and he said, "Well, whenever you get something so close, there's a little bit of luck in it." And he said, "But I never tell anybody that there's luck in it." And so there's probably always a little bit of luck in modeling. And are there other events where maybe we don't understand as well what's going on? And of course, unfortunately, we haven't, since 2017, had a LIGO neutron star merger event that was then followed up and discovered such a kilonova following it. There's been some interesting gravitational wave signals, but none that we've been able to find a counterpart to. But there are other ways to try to search for kilonova. One can look for the gamma ray burst that may be produced by those relativistic jets, and then follow those up to see if maybe they're were the result of a neutron-star merger and they have a kilonova afterglow. And that's what several groups have done. In 2023, there was this gamma ray burst that happened presumably in this galaxy, although the event, the gamma ray burst actually was very far separated from the galaxy itself, way on the outskirts of it. And they followed it up and found this very red glow after it, having the very characteristic red color of a kilonova, the heavy opacities of these heavy elements. And that was intriguing. They got some more data on it, some observations of the light curve in optical and infrared, and even farther infrared data. These dots are the light curves of that 2017 event, which are very well sampled. This data is much more sparse, but you can see it basically follows the same sort of trend, a fairly very sharp decline in the optical emission and a slower decline in the infrared bands, a very red event that gets even redder over time. Sort of looks like this kilonova from a neutron star merger, perhaps a little bit brighter. And there's been a couple other events that show a similar behavior in the follow-up gamma ray bursts. Now it seems pretty compelling. There was two puzzles that came out of this event that might indicate that there's something that we don't fully understand about kilonova, or at least events of this sort. The first was that the gamma ray burst that happened here was not a short gamma ray burst. It was a very long one, or at least much longer than usual. It lasted, a minute's time scale instead of a typical seconds time scale. And given that the natural time scale for material orbiting and accreting onto a black hole in a neutron star merger, we said was about a second, it seems hard to explain why the gamma rays that are coming out of this thing would last so much longer. The second puzzle corresponds to the emission from the kilonova itself. In addition to this data here, in the optical infrared, they were able to observe this event with JWST at longer times at longer wavelengths, and compare to data that was taken by Monsi here for 98 PW using Spitzer. And so they were able to get even spectral information at these late times using the new capabilities of James Webb, giving it a chance to look for the first time at what such an event would look like 30 days after the event first took place. And here's the spectrum that was observed, appeared in these papers. In the blue, we see kind of light that's produced from the gamma ray burst itself and its afterglow. But at longer wavelengths, we see this, what looks like thermal emission from a black body in the infrared wavelengths that has a luminosity that you would sort of expect for a radioactive kilonova. It has a temperature of that black body of about 800 Kelvin, which if you ask what the radius of the emitter at that temperature should be to match the luminosity, it gives you something roughly equal to the radius you'd expect for something moving at a few tenths of the speed of light for 30 days or so. So it seemed like a nice case for understanding this as observation of the radioactive cloud. The problem is that to understand, to produce a black body like this, you have to have an opaque medium where the photons can be thermalized and be produced from some optically thick photosphere. And at 30 days out of the explosion, this very low mass ejecta becomes very optically thin, and the opacities drop extraordinarily. So we can calculate the opacities of this kind of mixture as a function of temperature for different amounts of these very high opacity lanthanide material. And you can see it has this interesting behavior where there's different peaks with temperature. These correspond to the changes in ionization state of the plasma as the temperature changes. But as we get to these low temperatures that we're observing now, the opacities tends to plummet. In thermal equilibrium, it predicts that all the atoms should become neutral, and it becomes very hard to excite any of the levels that produce the line transitions that give us the opacity. And so, similar to Robert Christy's study of the opacity of hydrogen and how it changed at the ionization of hydrogen, here we see the ionization to neutral drops the opacity extraordinarily, producing a very optically thin medium. Looking at in more detail, if you calculate the opacity of this sort of our process cloud, at early times when it's rather dense, you get a rather high opacity as a function of wavelength all the way out through the mid-infrared. But at these later times where things are colder and the density is low, the opacity here are orders of magnitude less than you would need to produce this kind of thermal emission. Instead, you just see maybe a few strong scattered lines about at the wavelengths that are being observed. So we can calculate or try to calculate what we'd expect the emission to be at these late phases using those same radiation transfer techniques. And what you get out is not so surprising. You don't get out a nice black body, you get out some sort of nebular type spectrum where the emission comes out in individual lines. Those lines are very broad because of the high velocities of the material or Doppler broadening them. And there's a lot of lines that blend together. But qualitatively, we expect things to look something like this as the material becomes optically thin. There's a lot of uncertainty in the atomic data and the exact appearance of where these lines would appear. But the general behavior is probably of this sort, as other calculations by Fukuzaka has seen as well. So it doesn't seem to give us the optically thick behavior that we would expect. You might ask if in these very radioactive environments, is this assumption that particles would be in thermal equilibrium violated? And indeed it is. A study by grad student Daniel Breithauer has looked into this and noted that in these radioactive environments, the fast electrons that are produced in the beta decay will come through and ionize atoms. So even if the temperature is low, this continuing ionization by radioactive products can keep it ionized for some period and change the results in some significant way. And here's some calculations he's done of the light curves at earlier times in all different wavelength bands. The solid lines being including these non-thermal effects and the lighter lines being ignoring them. And you see it does have a significant effect on the results, especially in optical bands where the system does remain brighter for some period of time. It remains more ionized and with lower opacity. So this is certainly an important effect to include when analyzing the light curves such as that of the 2017 event and trying to extract the amounts of heavy elements that were produced in such events. And indeed, we can generally get better fits to that sort of data when we include these effects. But it doesn't change the qualitative features of this. In fact, this was calculated using those non-thermal physics effects. And yet it doesn't change the fact that at these late times, we expect to have a very optically thin medium. So what could we be seeing here? Well, maybe there's some physics we're missing, some sort of opacity of some sort that's missing that will explain why we can't explain the spectrum of this event at late times. Or maybe we are talking about something totally different indeed. If we put together these two puzzles of the longer gamma ray burst and the strange late time spectral behavior, we might imagine various other systems that could produce something like a kilonova without actually being a kilonova. And one thing that might be interesting would be going back to those white dwarf stars and asking what happens if their companion is not a donor, but a neutron star or black hole that as they merge, rips the white dwarf apart. And interesting, the physics has some similarity to what we've already looked at. You tear apart the star, you might eject a little bit of it, you create some disk. But now the scales are much bigger. This disk will be tens of thousands of kilometers instead of maybe a few hundred. The time scale for it to viscously accrete will be on the order of hundreds or thousands of seconds, more naturally in the time scales that are seen for the observed gamma ray burst. And the composition will be quite different as well. It'll be just equal numbers of protons and neutrons. Hasn't been much work on this, but some simulations indicate that in this process, you get something of a deconstructed type 1a supernova, where inner material here gets hot and burns into nickel, and then just gets ejected in a wind, mostly along the polar regions, while material further out might not burn as much or not burn at all and get ejected. So we get this interesting structure where maybe we have heavier elements on the outside moving more quickly and a lot of carbon and oxygen from the original star mixed throughout. The masses ejected can be larger and the nickel mass is about 1% or so. No R process or other elements heavier than iron expected to be produced. So if the opacities are, we don't have this heavy opacity of the heavy elements, R process elements, isn't this problem even worse? We won't be able to explain the opaque late time observations. That's true unless we suggest that maybe there's some other physics that we're missing, some other sort of opacity. And in ejection of carbon oxygen white dwarfs or in type 1a supernova, as well as other sorts of systems, one sees dust, grains of dust forming in the clouds that get ejected. This is, again, this Cepheid star that, in addition to pulsing, had apparently some material get blown off in the process. And in that, gas is formed into little particles of dust that are reflecting or getting heated up and radiating the light from the central star. So we see this kind of dust formation happening in mass ejections. Here we have a system that may produce a lot of carbon and oxygen. And if we have some excess, say, of carbon, conditions may be right to form a sort of carbon dust, which can happen if the temperatures drop below some condensation temperature of 1500 Kelvin or so. It would start by two carbon atoms bonding together. That's sort of the rate limiting step because it takes a long time for them to bond together since they have no electric dipole to radiate the extra energy off. But once you start forming some of these dimers, it's much easier to then accrete other carbon atoms, and you can build up your dust grains quite quickly. The cross sections approximately, well, it'll be in this limit where the cross sections are just going to scale like 1 over the wavelength and depend upon the radius of those grains. Well, the radius would have to be calculated in detail. Actually, the opacity, the cross section per unit mass, it cancels out and really has a simple form as a first order approximation. So if we assume some of that dust forms, well, we can include in our radiation transfer code some treatment of these sort of reactions happening when the temperatures drop. And we can look at some spherical model at which we have carbon and oxygen, nickel and other elements, and evolve it over time and see where we might expect dust to form. Dust initially forming in the inner regions of the ejecta where conditions are rather cold. As it heats up, some of that dust gets destroyed, but then reforms again at later times until we have some reasonable fraction throughout regions where carbon may be abundant. And those dust grains are actually quite opaque to optical infrared light with opacities that are sufficient to keep this system optically thick at later times. And if we model the synthetic spectrum, we see we can get a dust re-radiated, fairly thermal black body that does a reasonable job matching these JWST observations. It would be nice if we could get observations at longer wavelengths to see if it really does follow such a black body. But it's an improvement over the predictions of a nominal kilonova model of heavy R process elements. We don't get this peak here, this apparent line emission feature, which has been argued to be a feature due to heavy elements like tellurium. So it remained to be seen what sort of element could produce such a line here, and that may be a weakness of the model. But we can get the rough continuum properties of that spectrum. You can ask if we can get the light curve of the event well. Like a regular kilonova, it was found to decline very quickly with time. And if you look at the radioactive decay of nickel, it's actually a very slow process given its long half-life. And so there seems to be a big mismatch between the nickel decay time and the actual energy that they saw radiated. But we have to keep in mind that the nickel decay produces primarily gamma rays that then get absorbed in the ejecta and heated and re-radiated as this black body. But in these fast low density outflows, those gamma rays can escape and emit as gamma rays that we'll never see and fail to energize the ejecta cloud. And at early times, it's dense enough that those gamma rays will be trapped, but increasingly over time, they'll be less trapped. And so if we calculate that effect in our models, we see that actually the light curves declines much faster than the nominal decay of nickel with a speed that is reasonably consistent with that fast decline. So this decline here is due to the escape gamma rays. At late times, this is even faster. At late times, the emission here, all the gamma rays are escaping, and the ejecta is being heated by a positron produced in the inverse beta decay of cobalt. But that itself may not thermalize effectively. It may fail to heat the ejecta if the densities are too low. And if we include some treatment of that, similar to how we treated in kilonova models, we have even a faster decline. So this is sort of a tuned model that was able to get certain ejecta mass and nickel mass and velocities that were able to roughly reproduce the observed light curve in spectra. But the values inferred are not unrealistic for a white dwarf merger, and the assumption of dust formation at these later times could help explain things. There is this issue of the line. Now, what kind of extra lines might you expect to come out in a system like this? There may be molecular lines that are produced, in particular the carbon and oxygen. They produce carbon and oxygen lines. There are two bands of carbon and oxygen, one appearing here where it seems like there's potentially some excess emission. One appearing here that's close to this line feature, but a little too red to explain it. You might argue that some blue shift due to some velocity might bring those into agreement. We could try to include this carbon-oxygen molecule formation and emission in these radiation transfer simulations as well to see if it appears. Depends on how much carbon and oxygen you think forms in the ejecta. But one issue you find is that due to these carbon and oxygen bands, which are due to rotations, vibrational rotations of the carbon and oxygen molecule, this fundamental one here at longer wavelengths is always stronger generally than the one at shorter wavelengths. So even if you set up conditions where this line is still weak, you'll get too large a line at longer wavelengths. So it could be this bump in the spectrum here could be related potentially to carbon and oxygen. CO molecules, but it seems difficult to explain this one with it. So it remains something of a mystery what could be producing that line feature. And it remains something of a speculation that these new events that we're seeing that people are calling kilonova are actually white dwarf neutron star or black hole mergers, as opposed to something else. It still seems quite plausible that these new events could be neutron star mergers and regular kilonova. We'd have to explain these two puzzles that I mentioned. One, the long gamma ray burst, but there's been work in simulations that, like the ones I showed you of the accretion disk and relativistic jet that were formed, done by Gottlieb, that show that it can be possible under certain conditions to make the jet last longer of minutes time scale if we have the right magnetic field structure. The magnetic field, the behavior can dominate the jet production power more than the rate of accretion. So it may be possible to get a long gamma ray burst from a neutron star merger, contrary to what was generally thought. And maybe that's the explanation here. We still need to explain why we have this opaque system at late times when our kilonova models predict it wasn't. There we would have to maybe evoke the same physics I just mentioned, that say dust was formed in the kilonova itself. And it's a heavy unknown whether in this sort of radioactive waste cloud you expect dust to form at some point. But it's something we've been studying with Kento Hodegizaka and Nade Donato at the University of Tokyo. The process could happen in a similar way that I described. There's some refractory elements that are produced in the R process that may be able to, at low enough temperatures, for pairs and eventually maybe nanograins or something like that. And we're defining the conditions, but the conditions could potentially be such that you get enough dust at these late times to produce enough opacity to explain these late time data. In that case, our kilonova may be red in part because they're dusty. We're looking through a dusty cloud. There's other possibilities that I didn't talk about, whether some massive star collapse could produce something of the sort. Those could naturally produce long gamma ray bursts, but it seems very difficult for them to explain these very fast kilonova-like transients, and very hard to explain why such a massive star would be sitting so far out from its host galaxy. And we have something like a white dwarf merger, or maybe there's other sorts of white dwarf phenomena that do similar things. The accretion-induced collapse of a white dwarf potentially leads to some ejection of matter, or other partial disruptions of white dwarfs that have been suggested. And they can do something that's qualitatively similar, but whether it's the right application here, we'll see. But one thing we can say is that events like this are plausibly out there, even if they're not this particular event. That in the universe out there that we're searching, there may be several, low mass ejections that are producing kind of fast red transients that may serve as kilonova imposters. And we'll have to keep that in mind as we start to search the sky at red and infrared wavelengths, and hoping to find in our search things that might look like kilonova and might indicate neutron star mergers, that there may be other things out there as well. So I'll finish there, just mentioning again how all this the simulation work is really extensions of the early work that we saw, very similar physics and behavior. And it's been a great pleasure to be able to come talk to you about it. So thank you very much.
Great. There are many subluminous 1A supernovae which lead only 0.1 solar mass of nickel or less. So
Mhm.
the carbon oxygen in those are unburned.
Right.
Okay, so why don't they all do the same as well, whatever explaining things like this?
Well, are you saying you have late time data that where you don't see?
Or if I just apply it,
Mhm.
yeah, 0.1 solar mass in nickel, the rest is all carbon oxygen, they'll form dust, they'll do all this stuff. Why does it happen?
Yeah, well, we'd have to, yeah, there may be cases like that where maybe empirically it doesn't happen. Or maybe the conditions are different. The carbon oxygen ratio is important for determining how much carbon is left after you've made CO to make grains. And the conditions of dust require certain temperatures and densities and may be quite sensitive to the exact conditions. But that's a good test to see if there are events that seem to be in the range where we expect this to happen and constrain actually the physics of potential dust formation. If there are, it's a good question to ask if there are events where you would expect to have seen this or you're somehow biased against seeing things that might have formed dust at late times.
Because silicon oxide and carbon, silicon carbide also features.
Yeah, here just assume carbon dust, a simple cross section. But yeah, if you assume that there's silicate dust that forms, there are features in the near infrared that do appear, emission features at 7 microns or so. So we see those if we use a different kind of dust, and those would be signatures of a certain dust.
Curious about the sort of white dwarf neutron star or accretion-induced collapse time models for this GRB, long GRB that you were mentioning. Basically, I'm wondering, is there any complementary constraint you can get in the presence of the neutron star in that system afterwards? The reason I'm asking is that if you look at a lot of work has been done both for neutron star mergers, so also recent simulations, I think some of which you were involved in for accretion-induced collapse, or also for, if I look at white dwarf mergers, I can get quite substantial amplification of magnetic field in the outer layers of this object, potential launching of relativistic outflows once we form that. So I wonder if you just find any evidence for additional energy injection from the central neutron star. So it's like a huge to distinguish that thing from like a black hole.
You're saying on longer time scales than the GRBs, like even right on this.
Any evidence of a neutron star remnant anyway that you could additionally constrain, either by the emission or just by the energy.
Yeah, I guess you're saying if we have sort of a longer lived magnetar or something that it could spin down and energize this thing and produce an alternative set of power to the radioactivity itself. And that could be an alternative to the nickel for powering the event. And we haven't done that specifically. It'd be interesting to see if that could be an explanation of what's going on.
Because you wouldn't get that for like neutron star black hole.
You wouldn't get that for
neutron star black hole. I mean, it's a very clear sort of scientific neutron star.
Right. Yeah. If you could get some clean evidence of that, I think it might be you have to see if it's kind of fine-tuned to get the right parameters of that central engine to do it. But it's definitely an interesting thing to try to calculate to see if what parameters you would need. Yeah.
Once the things above the Kilonovae, right?
Yeah.
Can I ask my question? So there is one more clue for your 23 VFI mystery. Recently, the Zwicky Transient Facility had a type 1c broadline supernova for which we got a Keck spectrum, and it shows the same crazy red continuum in K band, which made us dust. It also had like 200 days has a bump in a similar phase, but that bump we think is sodium, not tellurium.
So there is
another line there.
There's another line there. That's great news to hear. Yeah. Yeah. Okay, that's fantastic. Yeah, that's great to hear. There's others. Yeah, I could have shown this. I forgot. Should, but they have seen signatures of this sort of dust formation in transit. These recent JWST observations of a type 1a supernova at very late times, you know, I think 300 plus days after the explosion. And you see here a sort of line nebular type spectrum in the optical. It was similar to the model spectrum I showed you before, that for optically thin material, you tend to see these sort of just line emission spectrum. But in the infrared, you see a very similar sort of black body. So here's a type 1a supernova, which is another white dwarf, carbon oxygen white dwarf exploding, that at some point in its life apparently does form dust and forms this infrared continuum. And the conditions here, it's much later, 300 days instead of 30 days. But the mass of a type 1a is many times, many orders of magnitude greater than a couple orders of order of magnitude greater than the models of a white dwarf merger. So conditions might be somewhat similar if you scale them out. So this kind of thing does happen in some events, but as she said, there may be other events where it doesn't apparently happen. So it remains to be seen if it's a ubiquitous type effect, which we should expect in some of these events, or whether it's more specialized conditions. But it's great to hear that it is also happening in the type 1c supernova.
The question of the possible dust formation and the Kilonova with dust,
right?
Or something. Is there a particular reason why that seems much harder? I mean, if you rapidly expand, I don't think it's particles. There's no oxygen or carbon or something to make other molecules. So is there a reason for thinking that it would?
Yeah, maybe it's hard. I think the densities are lower. So in these white dwarf merger outflows, we can have maybe a few tenths of a solar mass instead of a few 5/100ths of a solar mass, and the velocities are presumably lower. We have higher density, so that makes it a little easy to nucleate these things. But yeah, you might be right. And we're studying this, and it seems like if you're not too low density or too high velocity, there's a lot of uncertainty, but it seems like you may be able to form these sort of metal dusts out there, and there's enough refractory elements that it could be enough to explain these things. So I think that's still a plausible explanation of what's going on.
Regarding one is, does the simulation indicate a donation or just where would it become?
In which event the neutron star white dwarf? Yeah, it's something in need of further numerical study. These are older simulations by Rodrigo Fernandez modeled the disk accretion, and it's really a result of the idea of carbon oxygen disk, but when it gets kind of close to the black hole, the temperatures get high, and you get sort of I wouldn't call it a detonation, but you get burning to nuclear statistical equilibrium as you blow it off. So it remains a sort of a quasi-stable type of accretion, but there are certain conditions where you are hot enough to burn to nickel. And of course, the exact amount of nickel you'll get out depends upon the conditions, the mass of that disk, and other things. So there can be a lot of variance in the type of behavior you might get out. Yeah.
Well, I just want to say dust formation is very common in super.
Right.
So, for example, in 1987, we had one we don't see what is very because of dust formation.
Yeah.
Well, when most of the gas is low velocity descent, stands slower, and it has all these metals that are usually rich.
Yeah.
Then it gets distorted with the reverse shock.
Yeah.
So that's usually yes, good types of dust. Question that is, I think, interesting. Why don't all super be so? Then I think the answer sense.
Right. Yeah.
We saw that was true. We were detecting supernova from tens of years ago.
Yeah, I'm saying that's a very
Yeah.
So it could vary with the right, it could be very common, we just don't have enough constraints on.
Yeah. Yeah, but you're right. They're seeing a lot of dust in massive stars. I'll mention that when I gave a talk, I don't remember when, it's like 2013. When I was first kind of describing the physics of kilonova, the opacities and colors of kilonova. And I remember the first question that I got asked was from Shri, who said, "Well, is dust going to form in these kilonova? You get very cold." And I said, "I have no idea. I don't know. That they're very low density." And then I think that question was forgotten for I forgot about it for a decade or so, and until there seemed to be this sort of event where I couldn't think of any other idea for what may be producing this infrared behavior. So you may have had the insight at the very initial stages. Yeah.